Good morning and welcome to your free physics tutorials. Now let's go quantum. When talking about quantum physics, there are lots of different interpretations. One is called the Copenhagen interpretation, and it was formulated by Niels Bohr and Werner Heisenberg. The Copenhagen interpretation states that the wave function does not have a physical nature, and is instead comprised of pure possibility. It suggests that a particle traveling through the double-slit experiment exists only as a wave of possible locations that ultimately encompasses all possible paths. Only when the particle is detected are the location and the path it took to get there decided. The measurement is a transition from the possible to the definite and is called the collapse of the wave function. Niels and Bohr suggest that prior to collapse, it is meaningless to try and define a particle's properties. All of the possibilities within the wave are interacting with each other and increase the chance that some become real and decrease the chance of others. Okay, so I have a red marker and a blue marker. So we know that. And if I put them behind my back, now you don't know where they are. So there's sort of endless possibilities. It could be in my left hand or my right hand. And we won't know which hand it's in until we measure it. So if we measure it, red is in right hand, blue is in left hand. So that's like the collapse of the wave function. We didn't know until we measured it, and until then, it could have been anything. To sum that up, the Copenhagen interpretation states that the precise position and momentum of a particle cannot be measured at the same time. You can know the position or the momentum, but not both. This transitions into Heisenberg's uncertainty principle, which is based off of the Copenhagen interpretation by one of its creators, Werner Heisenberg. Heisenberg's uncertainty principle shows that quantum systems are probabilistic, not deterministic, and furthers the idea that one cannot know the value of position and momentum at the same time. The more you know about one value, the less you know about the other. Heisenberg's uncertainty principle is as follows. Okay, so Heisenberg's uncertainty principle. We know that uncertainty in position times uncertainty in momentum is greater than or equal to Planck's constant over 4 pi. So from this equation, we can gather that position and momentum are inversely proportional. So we're going to do some super simple math to think about this. So let's say that the uncertainty in position is 2, and we know that, let's say, we know that Planck's constant equals 6.626 times 10 to the negative 34th, but in this situation, let's just say that Planck's constant is equal to, let's say, 16 pi. So then if Planck's constant is equal to 16 pi, we plug that in, change in x, change in p greater than or equal to h over 4 pi. Then we have 2 times change in p equals 16 pi over 4 pi, which then means that 2 change in p is equal to 4. So then we divide that by 2, so change in p equals 2. But obviously, because Planck's constant is constant, say that we did that, but change in x was equal to 4. Then you've got 4 times change in p equals 16 pi over 4 pi, which is, then we know 4. So 4 change in p equals 4 divided by 4. Change in p is equal to 1. So when we look at that, when the change in x went up, the change in p went down, which means that when the uncertainty of x increases, so when we know less about x, then the more we know about p because the uncertainty in p is decreasing. So let's do an example problem. Let's say an electron is traveling at 6 meters per second, and there is 15% uncertainty about this velocity. And we want to know what the uncertainty for position is. So we know that to find, if we're given a velocity, then we would need to find the momentum. And so momentum is equal to P equals m over v. So P equals, we know that the mass of an electron is 9.2 times 10 to the negative 34th, so 9.2 times 10 to the negative 34th, times the velocity that we were given, negative 31st, excuse me, negative 31st, times 6. And then we also want to multiply that by the uncertainty, which is going to be 0.15. So then if you do that math on your calculator, we'll end up getting 8.28 times 10 to the negative 31st. And now we can just plug in. So we know change in x times 8.28 times 10 to the negative 31st is going to be greater than or equal to 6.26 times 10 to the negative 34th, which is Planck's constant, 6.626, over 4 pi. And then if we do that math, then you end up getting, this is one number, so you can just divide by 8.28 times 10 to the negative 31st on both sides. 8.28 times 10 to the negative 31st. And you'll end up getting change in x is greater than or equal to 6.4 times 10 to the negative 5th.